Thanks for being patient, and get ready for Beam to the future. Some old ideas made new. So given that this is a talk about looking back in a lot of ways, this is the obligatory quote about having to look back in order to move forwards. And one more from Perlis. He has this really lovely list of about 110 epigrams on programming. So many good ideas are never heard from again once they embark in a voyage on the semantic gulf. So let's talk a little bit about this talk. And let's start with, why am I up here talking to you? So my name is Zelenka. You can find me on the internet pretty much everywhere as XP'd. I'm the co-founder and CTO of a company called Fission. We're building the future of web-native apps. That's applications that run entirely self-sufficiently in a browser. You can think of this as post-serverless or post-cloud. I heard somebody recently refer to this as blue sky as opposed to cloud, because it's a clear sky. And our goal is to make backend and DevOps obsolete, which is going to make me not very popular in this room. But don't worry, this is still pretty heavy R&D stuff, so you're safe for a little bit. I'm a programming language theorist and virtual machine. I used to say enthusiast, but I guess I've actually done work in that now, so virtual machine designer. And most recently, I got to use that work when I was a Ethereum core developer, which is, if you're not familiar with Ethereum, it's the second largest public blockchain. The twist on it versus something like Bitcoin is it's fully programmable. So really mainly just doing standards work there, all through the stack, but a lot of virtual machine stuff. I'm from Vancouver, where I founded the Vancouver Functional Programming Meetup and Van Beam. And in this community, I'm mostly known for a couple libraries. There's a suite called Witchcraft. It's, yay, about 5 or 6 libraries that port in a lot of ideas from Haskell and other MLs into Elixir. And like, monads, async map, all of that stuff. And Exceptional, which is an error handling library that lets you do happy path programming and handle your errors at the very end. It's a little bit like the with keyword, but you don't have to do all the manual threading yourself. So the sort of tagline online for this conference is Discover the Future of Erlang and Elixir, and we're talking about the past, which seems a little bit strange. So why this topic? I've given a few talks that are based around sort of classic papers. Go-to is considered harmful, or talking about 4th and 5th generation languages. And people come up to me after and say like, oh, that was a really good idea. It's nice that we can apply that now. That applies to the thing I'm doing today, but I wasn't aware of it until now, right? I've been reinventing the wheel. So is there some way that we can take these old ideas and bring them in as a way to move the rest of it forward? I was just at breakfast this morning chatting with someone who said, it's like the rest of the world now is discovering all the stuff that we've been doing in Erlang for the last 30 years, right? Are there other things that we can take from elsewhere and bring them into our ecosystem too? Selfishly, I want to push these ideas into other people's heads. So this isn't like concrete, here's how to refactor your code today, right? This is just conceptual. I want to push these into other people's heads so that we can start having conversations about other ways of doing things in the Beam and how we can evolve the Beam over time, because it's a little bit hard because the Beam does so much right? And sometimes you have to explore around other areas, especially as we get more languages and more paradigms into the system, right? Elixir and Erlang are pretty similar, but there are some less similar languages popping up. Alpaca is an ML, right? LFE is a Lisp. So how are we going to move forward as an ecosystem, cross-language and cross-paradigm, if we don't know what we don't know, if we haven't explored the studio space, right? What if we're stuck in a local maxima? which we certainly are, because when designing things, you're doing a totally blind breadth-first search through a design space. So you end up here, and sometimes you gotta go rummaging around in some less great ideas before you can make your way to the next paradigm. Spoiler warning, the three main things that we're going to be talking about are breaking out of linear thinking, or the von Neumann architecture, right? New types of modularity for the beam, and composable languages. So, in the beginning, this is another epigram. Says, it's sometimes difficult to find the correct unit of time to measure progress in programming. Some cathedrals took over a century to complete. Imagine the grandeur and scope of a program that would take that long to create. And really, those end up being the fundamental building blocks that we're going to build further things on top of, right? The Beam and OTP broadly is a project that's been going on since the 80s, right? That is a long project. Right at the very beginning, we had just hardware, and then machine code and assembly, and we eventually got to higher level languages. The first widely used one was Fortran, which most people would consider low level, but for the time was a very high level language. And to put it in perspective, the main computing interface at the time was the punch card, and people were listening to Elvis' Heartbreak Hotel. 29 years go by, and we get Erlang. Computing now looks more like what we would really consider to be a computer, right? You know, this is the Apple IIIC, which was released that year. People listening to Madonna, it feels much more modern. But it doesn't sound like a long time, but 29 years is a good chunk of time, right? Later that year, I'm born. Just to give you a sense of scale here, right? And that's not to make anybody feel old, which I realize that we're in a room called OK Beamer. You know, just to give you an idea of the size that we're dealing with here. Here we are, 33, 34 years later, at CodeBeam SF. Most people's computing device fits in their pockets. I'm now too old to really be up with the cool stuff, but I'm told that Taylor Swift is very popular. So that's a lot of time, and a lot of stuff has happened in there. The 34-year chunk has had an exponential growth in the industry, the number of people involved, all the people in this room, right? We've explored a bunch of different things. So why are we going to be focusing on this first 29 years, more or less, right? And that is that history sort of propagates itself, right? You don't change, you know, completely all the time. You're just making little changes. So let's think a little bit about paradigms. Douglas Crockford, he's a major figure in the JS community, said that it's really difficult to distinguish a new paradigm from a really bad idea because the shiny new object is part of the old paradigm, right? We never completely shift out of the old thing. It's always just a slight variation, right? You only have so much novelty budget in your organization, and that changes depending on which company, right, and which project, but for the most part, people want something that looks somewhat familiar. This is a large part of why Elixir in particular has done so well, right? It had a lot of, it felt like Ruby, even though it's very different, right? And the same goes for things like Docker, right? We've been building the same style of LAMP architecture, like literally PHP, a database, and a web server, that basic architecture for 20, 25 years. So when we run into problems with it, we said we want to do as little as possible to change that. So we create a container to make sure that it will run the same on the cloud. And we can take complexity and can move it around, but now it's somebody else's problem. Right. And is this going to be the long-term solution, the 50-year solution to problems of deployment at scale? I don't think so, right? We're now seeing the shift to serverless, which is we're going to take a container and we're going to shrink it down to a single handler. It's the same slight variation, but just shrunk down. Larry Tesler passed away recently, sadly. The guy invented copy and paste, which is pretty great. He has the law of conservation of complexity. Every application has an inherent amount of complexity that can only be moved around, but not gotten rid of. So what are some of the trade-offs that we're making on the beam that, with some other design choices, we could change? So looking back through the evolutionary tree of programming languages and paradigms, where are some places that we could make cuts or pretend that there was a different outcome to history? Something else did well. We're going to be looking at 4 array-based languages, the applicative model of programming, the standard ML module system, which is now also in OCaml and Reason, and natural and business language. So we're going to start with something totally alien. Does anybody recognize this language? It's more than I expected. That's great. Yeah, it's APL. Does anybody know what this does? No? I'll give you a hint. Anyone? Game of life. Yeah, exactly. It's Conway's Game of Life. APL is an array-based language. It also does very well with matrices. So unlike, say, object-oriented programming, where the basic unit is the object, or functional programming, where the basic unit is a function, everything is based on arrays. This makes it a really nice fit for something where you have a giant grid that you need to go over and look at the neighbors and update. So we can express what is otherwise, like, it's not a massive task, but it's not a one-liner in most languages, very easily and succinctly. What can we learn about the beam from APL? So cellular automata, the game of life, and actors have a similarity, right? We have emergent behavior out of both of them, right? Each step is very, very simple, but reasoning about the whole system can become difficult, right? When we're doing things with gen servers, we're not looking at the system as a whole, we're looking at an individual call, right? It's hard to keep the whole thing in your head. You draw little diagrams, right? You need to run a VM in your head to reason at that level, right? You have to have a simulation going. And we can abstract some of this away, right? And we're starting to do that now. We have Broadway. We have concepts like arrows in other languages. But the trade-offs are very different. You don't have the granular control. The thing that makes APL work really well for this kind of thing is they have a succinct language for it. And by default, not everything, but by default, everything is parallelizable because it's an array. It's just collections. The universal scaling law, so most people are familiar with Amdahl's law, which says, as you increase parallelization, you get to diminishing returns. The universal scaling law says if there is a point of contention, some shared state that everyone needs to go and talk to, it actually drops back off because you have the coordination cost suddenly. Right? It's worse than having less parallelism, depending on the type of problem you're trying to solve. So can we get automatic parallelism in Elixir or Erlang? Absolutely, we can. Witchcraft has this. So we have an async map. It's a lot like enum map, but takes everything and just automatically shoves them into a task and gives you back the same result in the same order because it's essentially enum.map with some extra properties on it. And we get a performance speed up. Right? So something that's going to take, this is just a stand-in for a long-running process or a 500 millisecond process, but we can do 10,000 of them in a second. Right? This works because we have a shared nothing architecture. We just have a collection. This is great for embarrassingly parallel problems, and we can do a lot more with macros. in this as well. We can do analysis ahead of time of what we're going to be operating on. Is it a short list? Is it a long list? Do we need to have pre and post conditions? Do I, because something happened earlier in the code, need to check that something's available? No, I just know that it's available, right? So we can start pulling these things out. Once we have arrays, we can have tables. Table-oriented programming, or TOP, just happens to have the same letters as OTP, was fairly popular for a while. It's the reason why Excel is so popular. VisiCalc sold a bunch of computers, which is sort of the predecessor to Excel. It was the killer application in, say, the late 80s, early 90s. And we do use tables. We just don't think about them that way. So here's a naive implementation. We have a user with a couple fields on it. Here's a table with the same data. And then we just have a list of that. And we can see the fields as columns in the rows. Right? But now that we have this idea that, wait, I'm working with tables in memory, we can do all kinds of stuff, right? We can work with this in parallel. These are individual rows. We can work with all of the name fields at once, right? We're now in a two-dimensional space. So if I have data, like so, and I have functions as well, why can't I also map multiple functions over them in parallel? The actual functions in parallel too, as well as parallel data. Right? And we can do this because, again, we've changed the restrictions on the system. We're saying that there's no contention between them. So again, using Witchcraft as an example, we have provide as a function. So you give it a list of functions, and then you provide it a first and a second argument. And this is going to take all of the first values in the first provide as the first argument, and then provide in the second as the second argument, and give you back all of the combinations of those, fully in parallel. While we're thinking about tables, then, and now we have tables in our program, that means that we can take ecto and put it everywhere. Right? Relational algebra is super powerful. It's very well defined. We understand how it works. There's a reason that databases do so well. What if we took the same things and applied them in a higher level language to everything dealing with data? We would get potentially massive speed ups. We're not dealing in the small anymore. We're now dealing in the large. Let's talk about composition. We're functional programmers, right? We know about composition and modularity. These are all about symmetry, really, right? And breaking things apart into different dimensions. So symmetry is a complexity-reducing concept. Seek it everywhere. And you can't communicate complexity, only your awareness of it. So what exactly do we mean by composable? Right? The Beam has no concept of composition. We just have application. Functions are a way of talking about not just transformations of data, but it's almost like a piece of data with a hole in it that you're going to finish, right? But it's still, an application is that filling, or is the destruction of this abstraction. So what kind of composition do we have? Well, obviously we have function composition, also higher order functions. Those are both kinds of modularity. And then we have rules, like commutativity. And all of these together are kinds of orthogonality, right? So just like how we have a vertical and horizontal component to space, and then with the two, we can think of them separately, but we can put the two together and compose them and get a much more powerful thing in two-dimensional space. We can rearrange concepts by using these. So we have composition in the data dimension, right? Which is data structures, structs, lists, all of that. We have composition in the function dimension, which is what we end up talking about a lot in functional programming. And we can extend that slightly and then have data flow as well, do parallel composition. We can compose capabilities with higher order functions and also protocols. And we have orthogonality of execution as well. So because we're dealing in concurrency a lot, we start thinking about how things are executing and the rules between them, right? So this blue dot, over time, happens at some point between those two lines, and we don't really care when. And we can move around exactly when it happens in sequence, right? It doesn't really matter, right? That's not one of our assumptions in the system. So we can take in a totally parallel system and test it completely sequentially, debug it completely sequentially, and it'll still work, right? And we can even plug these in together like so. So here's a diagram of how data flow can happen, and then laying that out as a function, right? Fairly standard data flow stuff. So we can do all of this in Elixir today. That's great. My question is, how modular are our modules, right? And libraries, for that matter, right? They're really namespaces. They're just bags of functions and maybe a data structure or two, right? Libraries, everything's hard-coded as dependencies in libraries. If you want to swap out a dependency, you need to fork the entire thing, right? That's not great. Or you can encode it directly in there that it's going to call out to another, there'll be some runtime instantiation, right? And it will call out. We can get module-level modularity with higher order modules. So this is a simple example from a real-world use case. So a few years ago, I was working at an agency, and another team, subcontractors, had never seen Phoenix before, never used Elixir before, and we're building an app, and the deadline was coming, and it was the app was just not in a really good place. So handed it over, and we said, okay, well, we have about 10 days to get a working version of this. What's the fastest way that we can work and make it flexible? So we wrote a Phoenix vertical, which did the whole stack, right? Router, views, controller, the whole thing, with the ability to override individual pieces using the macro, right? And the ability to plug in other dependencies into it. So here's a def module with more arguments, where you can now pass in other dependencies. And we're giving it default dependencies as well, right? So for queries, we're going to have an ecto query. For the schema, we're going to use ecto schema. JSON's poison, right? This means that it needs a type as well. So we can now type our module, the interface to our module, because it's a function from modules to modules, and then call them inside the module as normal. We started calling these hot swappable dependencies, but this is an idea that's existed for about 35 or 40 years. So just like we have hot swappable code, now you don't have to fork everything all the time, right? We have modularity in our libraries. It's really not that hard to do this kind of thing. So in one of the witchcraft dependencies, or part of that project, is one called type class, which gives you protocols that can depend on each other, all checked at compile time and enforced. It won't compile if some piece of data doesn't have a protocol implemented on it that you say it needs. And it's about, that dependency piece is about 60 lines of code. The entire library is maybe 500, right? This is pretty straightforward to do. We don't need to change the compiler, nothing. It just kind of, this is the nice thing about having an extensible language, right? We have macros, we can send the language, and these things work really well. those types I was mentioning before are essentially behaviors. Right? We don't care about everything in the module. We just care about the pieces that we need. So behaviors actually end up with another use suddenly, right? A compile time use instead of just a runtime one. And finally, declarative embedded DSLs. It's the highest goal of a programming language to enable good ideas to be elegantly expressed, right? Not be stuck in the muck and in all of the details all the time. So domain-specific languages, we're familiar with them, right? Ecto's one. We use them. Some people say, well, you know, everything's a domain-specific language, right? Assembly is a DSL for coding computers, right? And I would say that there's a spectrum, right? There's no like exact delineation, but it's roughly between a language and a framework, right? It's something that has something to say as opposed to a toolbox of pieces. So, you know, using some operators. This is not a DSL, right? This is just library functions. This is just Elixir, right? But this starts to be a DSL, right? So this is LG. It's a data builder, both structs and some types, which we don't have natively in on the Beam. It generates for you a bunch of things, including default constructors, default arguments, the type, runtime checks for conditions, and you can override things like saying, you know, I want the numbers to be, you know, 1, 2, 3 instead of 0, 1, 2. Right? It actually really ends up being quite a nice fit for a lot of problems like, you know, in this case, a video game, right? We're going to have a, just describe the player character and the things that it can do. And we've now created a smaller version of the design space, right? It's not all the nitty-gritty details anymore. So how do we make this apply to business problems? What can we learn from that space? What can we learn from the dreaded COBOL? So for those unfamiliar, COBOL, Common Business Language, was a used from the sort of the, I guess, the 50s onwards, and has a fairly verbose syntax, which we'll look at in a moment, and got used in a lot of banks and places like that, and is still running today. And if you write COBOL, there's a good chance that you can get a big salary from going into these places and writing code because nobody wants to write it anymore. So, and it looks a whole lot like this. A lot of commands are multiple words. It's trying to kind of read like English, right? The big advantage here is that it's readable by non-coders. Right? You can get a general sense of what's going on. It's pretty straightforward. The complexity is you know, it's not very good at handling large complex systems, but it's very readable. So a few years ago, I was at a security token exchange, and they brought me in to write a formally verified language for doing blockchain-based stocks and bond trading cross-border. Our constraints were it had to be readable by lawyers, and it had to be formally verified at compile time, right? It had to be able to take things like the BC Securities Commission, the CRE Exchange, and the SEC rules and apply them in code and check that the code we're writing follows the rules, because nobody wants to go to jail. And we ended up with this unholy union of COBOL and Prolog that worked out actually surprisingly well, right? You can just write these things, and it has an algebra that it checks. And you know, it's very well defined, very clear what's going to happen. And not only can a lawyer read this, but the business folks were able to write this. Ben Church gave a talk in Elixir, at the Big Elixir earlier this year, where he wrote a DSL, an external DSL, where the business people were writing the business logic for doing scheduling at veterinarian clinics, right? And it was a small language and really just inequalities, things like that, right? But my gut reaction was, wouldn't they be afraid to do that? You know, programming is this scary thing. And no, they were perfectly happy to go in there and be like, oh, I don't have to wait a week for this change to happen. I can just change this. Oh, great, fantastic. And they felt empowered by it. So this kind of thing is really great for doing domain-driven design, right? We can communicate with the domain experts. We can make sure that they follow certain rules so that they are correct by construction. So that you can't express something that doesn't work, we can check them at compile time. Or at runtime, right? You can have pre and post conditions in there. And the big major advantage of this is it's a language that exactly fits your needs, no more, no less. No extraneous detail, and you don't need to extend it, and you can snap them together, right? Most of the ones that you see today are very inflexible, right? Ecto just kind of does Ecto things, right? It talks to a database, and that's sort of it. You can't work with it on, or I guess you could write a backend for it, but it's not really meant to work on other kinds of collections or be interleaved with other kinds of code. It's really meant for talking to a data store that lives over there somewhere. And this is called a shallow embedding. It's the quick and dirty way of doing a DSL. Right? You just use the built-in AST. What it can represent is limited. Or it's just some functions that provide a really nice subset of a language, but that they just run immediately, right? There's zero indirection between that and actually running it. Right? So the algae example I gave earlier is just a shallow embedding. Right? We get this nice syntax on the far right, and then that just turns directly into structs. Right? There's no in between. But remember the structure of these structs for a few slides from here. Deep embeddings are like a better AST. They come in 3 steps. You build a game plan, you optionally analyze and transform it, and then you tear it down. And you can tear it down in sequence, which is where the compositionality comes in. So building up a plan, so this is for doing those parallel pipes from earlier. It doesn't necessarily have to be structs, but because in this case we're doing so much of this at compile time, the runtime overhead doesn't really matter, and it's just easier to follow. So splitting and unsplitting in a declarative way, right? And we can make that read a little bit better by putting a nice syntax on it with some do's. And each line here is now going to be split, and then we're going to join them at the end. But that just generates this, right? Nothing else. And then we can take that and we can interpret it, right? So we can write our own AST now. We don't have to rely on the Elixir or the Beam AST, Beam bytecode at all, right? It's way more powerful. It's fully in your control. Using logic as data, so having this done in a data structure is much easier to look at and check than testing a bunch of functions, right? We can just look at it and say, like, is there an instruction in here that says to do this thing? Yes, great. We can test the thing that's going to transform it into actual running code separately, right? We have this modularity, this orthogonality again. You can do things like time travel debugging, right? You can keep that AST around as you execute and check when that went wrong, where was I in this, not stack trace, but in this data structure that's designed for what I'm doing. And I can even get it back into the nice syntax again. And the final one is unlike protocols, where you have a single canonical implementation, right? So we have one enum implementation for a list. We have one implementation for anything. You can pass these in as you need, right? Because it's just an interpreter. So here's a little a DSL composed out of several others, right? So you have a dog. It's going to move around, and we're going to print some messages. And we have several languages. We have movement, we have time, we have printing, and I'm setting the ANSI terminal. Right? Again, you can do the AST as a series of nested structs like that. And that's generally my go-to for this. But because in this case, it's just a single linear straight line program, we can think of this as being just a list. So we'll do that for simplicity's sake. So we just have now a bunch of different records in a list. Pretty straightforward. And the interpretation on this feels a lot like GenServer, right? We're going to handle text, and if we get something that we match and we understand, then we drop down to that one and execute it, right? Or at least place in the function that would if this is happening at compile time with the macro. And we do this again and again for the different DSLs that we're composing. So handle gameplay, handle movement, right? Handle the ANSI terminal. And and then you build an interpreter out of it in sequence, in whatever order you want them to get evaluated in. And it's pretty straightforward, right? It has the same layout as GenServer, right? We have a command, and we have an agent that's going to hold our states, and we're just going to pass them through. And now we can take this, add one more line, and it all just works. Which means now we can take libraries that ship just mini languages, not even necessarily the implementation, but just well-defined, structured ways of working, right? Movement, text, all of that, in a way that is trivial to mock, really easy to analyze, and that we can take and even say, I'm going to take these two, and I want an interpreter that does certain things based on if a command came before it, right? We can get really, really a lot of power here. Which brings me to, finally, making some new mistakes. I have 5 problems for the next 30 years of Beam. Hopefully more like 10, but we'll see. The first one's a freebie. We need WASM support. This is already underway, but we need client and edge Beam if we're going to survive and stay relevant, really. We need to lower the barrier to entry, right? Low code. DSLs, business people can write, right? Why are we the keepers of the technology, right? With this wall, right? The more people that can code, the better, right? It's the most powerful tool we've ever invented. We need better correctness tools. So there's a lot of people that are really excited about types these days. Types are one kind of static analysis. Dynamic analysis, also very important, and other kinds of formal methods. Automatic, dynamic, parallel evaluation. So determining at runtime whether or not something should be run sequentially or in parallel or concurrently. Again, getting out of the individual details. And finally, mobile agents, right? This is, actually the DSLs work very nicely with this too, where you get partway through some computation, and then you can ship it somewhere else and continue the execution. So instead of always putting data next to compute, we can put compute next to data. And one final parting thought, which is another epigram. Dealing with failure is easy, work hard to improve. Success is also easy to handle. You solved the wrong problem. So work hard to improve. Thank you.